Hey folks, Joseph Kursky here with you to examine earthquakes around the world as a level 3 deeper dive. Level 3. Not too scary, but a little bit deeper than what we've done in level 1 and level 2. Now, as elsewhere in this course, note that there's quite a bit of spatial thinking and content instruction that can be accomplished without signing in to any tool or service. Thus far, level 1 and level 2, you've not even signed in to ArcGIS Online, for example. The map is sitting in ArcGIS Online, but all the things we've done, you haven't had to log in or sign in. For level 3, though, since you will be using the analysis tools, you'll need to sign in to do that. So that's one distinction here with level 3. All right, so in your browser tab to the upper right of your earthquake map, go ahead and select Sign In. You'll receive a prompt upon doing so. If you've already altered the map, you've changed the symbology, you've changed the scale, it's going to say, hey, do you want to save this before you sign in, and you'll erase all of your changes. So you'll say, yeah, I do want to save the map. Now that you're signed in, number one, you can save your map, share your map, and you can even create story maps, presentations, and other web mapping applications from it. Number two, you have the analysis button to the upper left of the map, allowing you to do more in-depth analysis. Let's focus on just two analysis tools here as an illustration of the power available to you in these analysis tools. Let's use Find Existing Locations and Summarize Nearby. Find existing locations and summarize nearby. Okay, folks, you ready to go? All right, not hearing any dissension, let's go ahead and proceed. Spend a moment browsing through the I information buttons next to each of the analytical functions or analysis functions to get a sense for what each category of the analysis tools actually do. At the time of this writing, 6 analysis categories existed, and 1 to 7 analysis tools existed under each category for a total of about 35 analytical tools. So summarize data, find locations, data enrichment, analyze patterns, use proximity, and manage data. Sometimes when working with spatial technology, you're faced with too much data rather than too little, making it challenging to discern patterns. Finding existing locations is one way to focus on specific features in your maps. So now let's use analysis, find existing locations, and point to your earthquake's last 30 days map layer magnitude. So analysis, find existing locations, and point to your earthquake's last 30 days map layer magnitude as follows. What we're going to do is we're going to choose layer containing features you want to find using attribute and spatial queries. Earthquakes last 30 days, 2.5 magnitude and above. For number 2, pull up the query builder. This is going to let you pull up and create a expression, okay? As you've seen elsewhere, building simple statements fosters spatial thinking. It also fosters a little bit of thinking like a computer, thinking coding, okay? Logic, etc. Spatial technology skills as well, at the same time by allowing you to ask questions about the data. Enter an expression using the pull-down choices, as shown here, so your resulting expression will be mag is greater than 6. When done, add. Your expression gets placed into the Find Existing Locations dialog box, as shown here. In the remainder of the box, give the resulting layer a logical name, such as earthquakes greater than 6, today's date, for example, such as earthquakes greater than 6, 10 January 2019. Why include the date? Well, it comes down to understanding your data. Your earthquake layers are fed from the U.S. Geological Survey's Earthquake Center and are continually updating, but your new earthquake greater than 6 data layer does not update continually. It's a static snapshot. So a date will be very useful because then you'll know when you created it. Once you've named your file, you are ready for the last steps. Uncheck Use Current Map Extent and Run Analysis. Okay? All right, run analysis. Examine the result of your analysis in your newly created layer. How many records exist in your data set? What is the pattern of the earthquakes above 6 in magnitude? At the time I wrote this lesson, almost all of the large earthquakes were in the Pacific Ring of Fire, and 24 earthquakes had occurred in the past 30 days, as shown here. I fell into a burning ring of fire. All right, little Johnny Cash there for you. All right, now, You can perform many of the analysis functions with more than one expression. In this example, you asked the data for earthquakes above 6 in magnitude. You could have asked for those above 6 in magnitude and with a depth of more than 20 kilometers down, for example. So you can add things to the expression for even more power. The second analytical function that we will explore here might prove useful in a variety of geographic topics is to determine which features are near other features, in other words, proximity. That's key in geography, isn't it? Let's determine how many earthquakes have occurred within the last 30 days within 4,000 kilometers of Melbourne. To do this, first you need a point from which to compute a distance around Melbourne. This is known as the proximity or buffer zone. Once you create this zone, you'll then be able to determine the number of features inside that zone. Okay? So the zone first, and then how many features are inside of it. The easiest way to add a point to your map is to use the search box to the upper right of your map and search for Melbourne, Australia. Be sure to select the Australia one and not a different Melbourne, because you might get Melbourne, Florida, and get completely different results. Go ahead and add it to map notes as shown here. You'll see the place marker on your map and a new content item, map notes, as a map layer on the left side of your map. Next, determine how many earthquakes fall within your buffer zone. To do that, use analysis, summarize data, and summarize nearby. So analysis, summarize data, summarize nearby. First of all, choose the layer from which distances will be measured. What is that? That's your map note. Okay, that's your layer that you're going to choose to calculate from. And that's your layer containing Melbourne. Number 2, summarize the layer earthquakes last 30 days, 2.5 magnitude and above. Be sure not to summarize the layer of only the earthquakes over 6 in magnitude, but here consider all of the earthquakes. Number 3, summarize nearest features using line distance, 4,000 kilometers. Okay. Number 4, add the magnitude average and the depth average. Number 5, skip. No grouping necessary here. Number 6, name your new layer, earthquakes, last 30 days, Melbourne, 4,000 kilometers, current date. Where current date is today's date, or something else that's appropriate and will indicate to you what is 6 months from now when you may have forgotten. And number 7, uncheck the use current map extent and run analysis. Now, once you are patient and let your new layer be created, and for it to draw on your map, quite a bit of information has to be calculated. Where's Melbourne? What's the distribution of earthquakes, the shape of the earth, etc. It will calculate it, and then you'll get a circle, kind of looks like an oval. It's a proximity polygon around Melbourne. And it's being drawn on a Webb Mercator projection, and that's why it appears oblong and not a perfect circle. So a little teachable moment there on map projections for the students. Now, check your polygon. Use the measure tool and measure the distance from Melbourne to the perimeter of your oval. As you saw in a previous component, and as you use the distance tool, the line you draw curves with the great circle route of the Earth as you move it across a long distance. However, the distance should be 4,000 kilometers from Melbourne to any point along the oval, even though it's oblong, again, because of the map projection. Because your new layer is a summary layer, the only thing it will draw on your map is your polygon at your specified distance, not any earthquakes. The power of the summary layer lies in its table, the I part of a GIS. Open the table for your new layer and examine its contents. It should look similar to this below, with the information for the past 30 days from the time you ran the analysis. How many earthquakes occurred within 4,000 kilometers of Melbourne, folks? In which country were most of them? Probably not in Australia, right? Not as many earthquakes in Australia, thank goodness, as in other places, but you've got other natural hazards there for sure. What's their average magnitude? What's their average depth? What percentage of the total number of earthquakes over the last 30 days were within 4,000 kilometers of Melbourne? To determine this, you would open the table of data for all the earthquakes, compare the number of features or rows against your new layer, and calculate the percentage within 4,000 kilometers of Melbourne. Now, at the time the lesson was created, 137 earthquakes above 2.5 in magnitude had occurred within 4,000 kilometers of Melbourne, with most in New Zealand, but some in Indonesia, East Timor, and the Solomon Islands, Vanuatu, and Papua New Guinea. And 137 divided by 2,079 times 100, meaning 6.5% of the world's 2.5 and above magnitude earthquakes occurred within 4,000 kilometers of Melbourne. 6.5%. Go ahead and save your map. If you'd like to see what the map should look relatively similar to at this point, go ahead and look at the one that I created here. Note that since this map uses layers resulting from analysis, you will need to sign in to view it. Okay, hopefully you're already signed in. Summary of our plate tectonics analysis. Congratulations. You have used 2 analytical tools in ArcGIS Online in this module's component. All of these analytical tools work in a similar fashion. They all ask you to name the input and the output layers, along with some parameters in the middle to calculate what you desire. So they all kind of walk you through in a step-by-step fashion. Step-by-step fashion, folks. You still with me? We're back again. Therefore, they're a powerful part of using spatial technology in education. Now, just as a small historical note, you used to have to actually run all these in command line mode. Some of you are like, command line mode? Well, now it gives you this nice wizard sort of workflow where it's prompting you, step 1, do this, step 2, do this, etc. So it's a lot easier now. Still, I recognize there's a learning curve here, so give yourself some time and patience. The most important tool, though, is not really this set of analysis tools in ArcGIS Online or whatever system you're using. The most important tool is this tool right here. Yeah, this tool right here, folks. Your brain and your students' brains. The analysis tools help you and your students, the real spatial analysts, that's what you are, to make sense of the Earth's phenomena. Without your evaluation and assessment, the computer tools are just widgets, and the data are just meaningless points, lines, polygons, grids, etc. You are the sense makers, the ones who turn tools and data into meaning. You're the sense makers. Excellent. We're going to add a couple of data sets to our earthquake map, okay? This touches on another wonderful capability in spatial technology, and that is to add additional data to your map. Think of our Lego bricks discussion. The data layers are like the bricks that you can add and remove to compare data layers of our wonderfully complex planet. You've already added data from your own information from your own computer, from ArcGIS Online, from the Living Atlas, from the field. So let's try something new and expand your skill set. Let's say you've already done some research and you've discovered with interest that tectonically, Australia is one of the fastest moving continents. Furthermore, you know that the URL of a map service that contains the rate of plate movement and another that shows the relative age of the ocean floor. So let's go ahead and use add layer from web, because you know the URL of the web service as follows. So inside, you've got your web map pulled up of the earthquakes, and you're logged in, you're signed into ArcGIS Online. So you can go ahead and add layer from web. In the dialog box that appears, select an ArcGIS server web service, and then paste the following pretty long, gnarly URL. This is a map service running plate movement. Nice. The cool thing is that you don't actually have to download it and then add it manually. You can actually add it while it's on the web. To understand it better, create labels and label the features based on speed in millimeters per year. Millimeters per year. Then OK. Observe the patterns using direction and speed. Wow, look at this. This is fascinating. So check out Australia. It's cruising. It's hauling to the north there. If Australia is moving according to this data set, key phrase, according to this data set, 68 millimeters per year on average, and the whole continent is not moving at the same rate, of course, but for the sake of integrating mathematics, how long would it take before Australia moves the length of your classroom? That's the kind of cool mathematical injection that you could do here, and lots more. Let's add one more layer. Hopefully this is getting you excited about the capabilities here. Let's add one more layer. Relative age of the ocean floor. Using the same procedures, use add layer from web, and ArcGIS server web service, and add this even longer URL. This is an ocean floor age layer. The ocean floor colors are given in relative terms, in millions of years, stored in the attribute grid code. Grid code. The ocean floor age bands away from where ocean floor material is produced in the mid-ocean ridges, getting older as one moves away from these ridges, as you probably know, until they are subducted back into the mantle in the subduction zones at the plate boundaries. in your contents to the left of your map, drag the relative motion layer over the top of your age of ocean floor. So you'll be able to see both the motion and the ocean floor layers. The motion in the ocean. Get it, folks? The motion in the ocean. Yeah, now your map should look similar to the following. Feel free to rename any of the map layers so they make more sense to you, such as relative plate motion and ocean floor, or ocean floor age. Save your map again. If you'd like to see an example of what your map should look like at this point, go ahead and look at mine. But I really want you to make your own, okay? Now, just one more thing. We live in a 3D world, hence, it makes sense to examine some geographic data in 3 dimensions, or even 4 by incorporating the time element. In a new tab in your web browser, open the following 3D scene of earthquakes for 1 month, right here. Think about, number 1, what is the value added in being able to analyze world earthquakes in 3D? What other data, city population, potential sea level rise, etc., would you want to examine in 3D? You can make your own 3D scenes. All right. Last couple bits here. First of all, back to the basics. Recall our discussion about the fact that more data is not always better. Yeah, we just added plate movement, right? And ocean age. Because you can add more things does not make it better. If you have questions that you want to have the students dig into, if you want to have them look at the motion and the age, great. Go ahead and add it. Easy to do. It took all of, 10 seconds to do it. But more is not always better. Something to keep in mind, okay? So as an example, in a new web browser tab, open the following web map of the most intense and the deadliest earthquakes in history. No sign-in required in this one. This map includes the 40 most intense earthquakes and the 15 deadliest. This simple map with 2 layers might be perfect for meeting your instructional goals. Okay, so that's a map I made. You could have made the same kind of map. It's just a simple map with 2 layers. It's got historical data in it. It's one of the reasons why I like it. Now, last piece, last thing to think about. Be critical of this historical earthquake data. Again, one of our themes of this module, be critical of the data, noting that some records are hundreds of years old and therefore are estimates of the injuries and fatalities. They need to be used, therefore, with caution. But still, the patterns tell an interesting story, don't they? Remember from an earlier discussion in this module that spatial technology through the ArcGIS platform allows you to access maps, apps, and layers, and that each has value. It may seem like digging into too much technical detail, but being familiar with how to work with all 3 is important in your work in spatial technology. In short, it gives you much more power and flexibility in your instruction, tailoring these maps and data sets to your own individual needs and goals. So, to illustrate, consider the first activity in this component where we examined earthquakes. After working through that, you have a map now of the last 30 days of earthquake activity, volcanoes, plate movement, and now the ocean floor relative age. A moment ago, in the above web map that we just examined, we have a map of the most deadliest and the most intense earthquakes throughout history. You can work with each of these maps as you need. The point here, folks, is that you've got some data available at your fingertips. They're not all created equal. For example, how did we know that the Lisbon earthquake of 1755 was so deadly? Well, we have eyewitness accounts. We have historical records. Do we have a seismic station that tells us exactly what that earthquake intensity? No, we don't have a seismic station that goes back 400 years. But, again, you've got a wealth of data at your fingertips, and as long as you're keeping at the forefront the limitations but also the benefits of being able to do this in an interactive mode, or you're asking questions, the students are answering, they're investigating, they're digging deeper, and I think it's a very compelling environment with which to teach. It's totally a problem-based learning kind of environment. That's indeed why spatial technologies were created in the first place. Thanks.